you have some certain vacuum, and then followed by a pressure wave. So vacuum, pressure, and then this hammering causes damage to the metal surface, and you end up with metal loss. Creep, and this is where you have a heater tube with high temperature and under stress, so this material starts to creep. And decarbonization, if you have environment with hydrogen, the steel might lose its carbon, and means that you lose your strength. Erosion, if you have sand in the stream, causes erosion. Graphitization, this is the carbon in the steel form graphite, so the steel loses strength, or it forms spheroidized in certain, I will show the picture. That's why your carbon steel, we don't use it above 800 because of this mechanism. Low temperature embrittlement, the materials at low temperature lose toughness, and it can break. So there is some rules how to avoid this. Mechanical fatigue, if you have a wire and you bend it several times, it breaks, so this mechanical fatigue. Some stainless steels, if you have high ferrite content, it can form a sigma phase at high temperature, and this, when you cool down, the steel becomes brittle and fails. Temporary embrittlement, the chrome moly steels, they are subject to this temporary embrittlement mechanism, which occurs at 650, 1100, and you lose ductility and failures. Thermal fatigue, it is again if you are cool, if you have a lot of cycles of heat and cool, this causes fatigue. Vibration also can cause fatigue. And the 885-degree embrittlement of this chrome steels and duplex steels can happen, becomes brittle. Some phase forms and makes it brittle. That's why we cannot use duplex above 600. This is a way of a pump, or some, looks like a pump. No, this is a casing of a pump. Erosion and a cavitation, and this is like an impeller. This is a brittle fracture, looks like from low temperature operation. This is a creep failure. Here a heater tube crept, and you can see the bulges. And this is how it cracks. This is a heater, HK14, in a reformer heater. This graphitization, this is the original structure of the steel, and if it goes graphitization, the carbon here leave the iron and make foam. Once it loses, and then this becomes a very weak steel. Or it makes spheroidization, it goes in certain areas. Again, it weakens the steel. Fatigue, typically fatigue, you can failure. Cracking happens gradually while it is in operations, and once it reaches certain thickness, it breaks all away, suddenly. Another thermal fatigue, it looks like thermal fatigue is up. Thermal fatigue means up and down, and it causes fatigue, and typical one of that, it is, this is the coke drum in a refinery where it bulges due to coke drum sees a lot of cycles. Every day it goes from high temperature and then goes to quench to dump the coke and so on. So it sees a lot of thermal cycles and causes this phenomenon. This is the microstructure of a crack. Again, another fatigue example, thermal fatigue. Gradual cracking and then all of a sudden shattering. And the same thing here. This is erosion. Looks like it has a coke. Coke, it is a particle that made this hole in this return bend or in this pump. It looks like it has cast iron with the cooling water. It has a lot of sand probably. Okay, I don't know what our break is what? We should have a break now, or do you have the look? Can you look around on the?
We've got 25 more minutes.
24 minutes? Okay. Material selection. No. So in order to do material selection, we need to know all the mechanisms I described before and realize where are you, and then we start selecting material for unit which on paper, not yet in operation. So we decide what is the design life. What is the design life we like to have? Normally we use 20 years for equipment, 10 years for piping. Some clients, they like to see 30 years here, 20 years here. So either this is what the normal way of doing it, but if the client wants something different, we apply with it. And then we try to find out what is the corrosion rate, what is the metal loss rate of the steel, of the metal. And the corrosion rate is expressed either in mils per year, MPOIs, or millimeter per year. And then once the corrosion allowance, then from that we can estimate the corrosion allowance from the life and the corrosion rate. Corrosion allowance means corrosion rate times design life. And the corrosion allowance we select between 160 and 1.8, depend on the service. But if we need more than 1/4 inch, we have to make upgrade for the material. This means carbon steel is no good, and you have to use different material. So how to find out corrosion rate? We use some references, published data, and recognized to be reasonable. And this one is for sulfide, sulfur in like crudinate, sulfur content, corrosion due to sulfur or sulfur compounds. And this curve was developed by McConaughey a long time ago, in the 60s. And it is a function of temperature, and you get corrosion rate for different materials. The lowest corrosion rate is stainless steel, the highest is carbon steel. As the temperature goes up, the corrosion rate goes up. So you have the temperature, and then you get the corrosion rate. And this curve is for 0.5% sulfur content. If you have a different sulfur content, you use this multiplier. You put your sulfur content on this line, and then you get the multipliers. We multiply this with the corrosion rate you got. And here is how it is. For certain temperature, you get corrosion rate. If it is different sulfur content, you use the multiplier. This chart is for hydrogen sulfide environment, like in hydrotreaters, hydrocrackers, reactor effluent systems. And this one is, I think, for carbon steel. It again is function of temperature with hydrogen sulfide mole percent or volume percent. And it gives you for this set of, this is like 1 mils per year, this 10 mils per year, this 45 mils per year. So depending on what temperature and what H2S, you get the corrosion rate here. And there is one for carbon steel, one for 5 chrome curve, one for 9 chrome, one for similar, one for stainless steel, and you use the corrosion rate for the material. And as you see here, carbon steel, this is a summary. Carbon steel give you the highest corrosion rate. And as you go by alloy, 9 chrome less, 13 chrome is less, but stainless steel is very low. So usually in such system, you switch from carbon steel to stainless steel because difference here between these materials are not much. Doesn't save you much of. For wet CO2, we use this guy, Dior Millam, Dutchman. He developed this monogram, which is basis for estimating corrosion rate in wet CO2 service as a function of CO2 partial pressure and temperature. You make this line, you get the corrosion rate, and if you are a high temperature, you get scaling factor because at high temperature, the scale forms and reduce corrosion. But this curve, if you use it, you end up using stainless steel everywhere. So it is very conservative data. And there are so many factors affecting CO2 corrosion other than temperature and CO2 partial pressure. For example, oil-gas ratio, the water content, water-gas content, pH, so many factors affect wet CO2 corrosion. And there is a software developed by Honeywell in Houston where we enter a lot of process data, like gas oil ratio, water cut, total pressure, H2S content, carbonate, if you know the carbonate content in the water, velocity, a lot of factors. And it gives you more reasonable corrosion rate. And this is what we tend to use, especially in gas systems. Oxidation, this table gives you some corrosion rate data for different materials at different temperatures. So usually we don't like to exceed 10 mils per year. So if you So if you are above 10 mils, you have to use a higher alloy and so on. This is based on that. There is the maximum limits for different alloys, especially it is used in heater tubes. So carbon steel, you should not use it above 1,000. Carbon half moly, you should not use it more than 1,100, and so on. Stainless steel can work up to 1,500. If you use 3HK40, you can use 1,850. And this is typically used in furnaces. Sulfuric acid also, this is typical for carbon steel, and it was developed by Dr. Fontana a long time ago. And you see the concentration of sulfuric acid and the temperature. And in this area, you get corrosion rate like 5 to 20 mils per year. In this area, you see the high concentration doesn't cause much corrosion, 0 to 5 mils per year. But the weak acid or the less concentrated acid causes much more corrosion. That's why you cannot use carbon steel in this area or lower. Yeah? And these are also corrosion rate of different materials. This high silicon iron, which we used a lot in sulfuric acid. This 316 stainless steel to give some protection, but not 100%. Alloy 20 is the workhorse for the sulfuric acid applications, as well as Hastelloy alloy, and there is Inconel 625 also is a good material for sulfuric acid. For pumps, we use the API 610 tables, which is give you, for certain service, give you the class of material to use. For example, if a boiler feed water, you have to use C6. C6, there's another table tell you what it is. C6 means 12 chrome, casing and impeller and trim. So this is a useful tool for us to use to select material for pumps. Here is a table and explains, for example, C6, 12 chrome impeller and 12 chrome impeller and casing. And here is the casing, 12 chrome, impeller is 12 chrome, and the other parts are all of it 12 chrome. So we can use this table. It is a good tool for hydrogen. For hydrogen service, we use this API 6941 graph, which was known as the Nelson curve. Any condition is a function of hydrogen partial pressure and the temperature. If you are below this curve, this is carbon steel curve, this is for 1 1/4 chrome, this is for 2 1/4 chrome, this one I think for 6 chrome. So if you are below this curve condition, your partial pressure and temperature, you can use carbon steel safely. But if you are above this curve, you cannot use carbon steel, otherwise it will crack by hydrogen attack. You have to use more alloy. The alloying elements are mainly chromium, and the chromium combines with the carbon, makes stable carbides that will not be attacked by the hydrogen. So we, as a function of temperature and hydrogen pressure, make. Of course, when you do that, we have to add some safety factors. We add 50 degrees for design, and we add 10% to the partial pressure, maximum partial pressure. For caustic service, we have this chart developed by NACE, I don't know, a long time ago. It's a function of caustic concentration and temperature. And if you are in this region, you can use carbon steel. If you're in this region, you have to use alloy, nickel alloy, otherwise you end up with cracking. If you are in this region, you have to use, you can use carbon steel, but you have to stress sleeve to avoid cracking. So these are tools we use to select materials. For wet H2S service, you hear always NACE for wet H2S, and there is a NACE document, original one, which is now used for upstream facilities like in Alaska. This one was developed maybe 2 years ago. It is similar to this one, but intended for refineries, because refineries, wet H is slightly different from the upstream. Upstream is more chlorides. Here we have ammonia with the ammonia and H2S, so there's slightly different environment. And for wet H2S, we have to stress leave at higher temperatures. You have to control your hardness. You have to perform traverse hardness tester for welding procedure qualification. There's a lot of material requirements for carbon steel or wet H2S, depending on the severity of the H2S. The higher the H2S, the more requirements. The medium, you have less requirements. If it is only not high H2S, you can just stress leave. We always require wet fluorescent magnetic particle of all welds after fabrication. This is a nice curve to define do you need protection or not. If you are below, this is again mole percent H2S, total pressure. If you are below this curve, it is not considered to be sour. If you are above this curve, you have to be careful. This for single phase, this one for multi-phase. For amine service, you need to amine service. Again, not all the amines are the same. The most aggressive amines are MEA and DA. Less aggressive, it is MDA and DGA and DEPA. And of course, the licensors, amines like Flexol, they have their own requirements. You have to heat treat all equipment. You have to heat all. Lean amine above 140. I think we missed one line. You have to rich amine. You have to rich amine piping. You have to heat treat all of them, and all equipment you have to heat. But for lean amine, you can relax. If it is temperature below 140, you don't have to heat treat. Maximum hardness again 200. You have to control your velocity in piping below maximum 6 feet per second. In areas of turbulence, vapor flashing, heat transfer surfaces, we have to use stainless steels, and I prefer to use 316 because of the moly. It is more resistant, and there is an API document give more details on this subject. When you go in hydrocrackers, hydrotreaters, you have to use heavy wall type reactors, as we are doing in Chevron job or El Segundo, I think. And we use chrome moly and chrome moly vanadium alloy steels for pressure vessels. And there are API documents that give the requirements for these steels, especially for heavy wall reactors. Because, as I mentioned before, the chrome moly, they tend to have a temper embrittlement, which means the steel become brittle after some time. We don't want the high-pressure equipment to fail due to embrittlement. So these documents, API 934, give you indication, give you requirements for heavy wall type reactors made from these materials. When you start using vanadium with the chrome moly, it generated some problems during fabrication, and this document gives some guidelines what to do during fabrication to avoid cracking during fabrication. They make a vessel, they make a weld, and they come next day in the morning, they found it cracked. So there are some precautions need to be done, otherwise you have problems. This document, it is being developed under balloting now with the API. This is for 1 1/4 chrome heavy wall reactors. This material is used mainly for hydrotreaters of naphtha, not high pressure, diesel type hydrotreaters. These are more heavy oil type reactors and hydrocrackers. This document is a report which about grade 91 still how to weld it, how to specify it. It was a big problem to control the welding of this material because it's tend to become very hard and tend to crack. So this report gives some indication how to. There's another report by API was developed for indication about duplex stainless steel. Duplex stainless steel also is a problem. If you don't weld it properly, it cracks. So you have to be careful with this material. Duplex stainless steel, it is, as I said, it's limited to 600, but also when you use it, you have to be careful how much chloride you have, otherwise you end up with stress corrosion cracking, or you end up with pitting. And for that, you have to be careful the limitation of these materials. And also, it also helps this curve, it helps that show you how stainless steel is very far below the duplex stainless steel, this one and the other one. Also, you notice here, the duplex stainless steel is here, and 316, 304, 316 is far below. So this gives you some good guidance how to select the material. How are in time now? 1 hour passed. We need a break now, or 10 minutes? Okay. reactor effluent